All right, so we're going to go through the last portion of our note sheet for this unit. We'll talk physical versus chemical changes. We'll talk about states of matter. You can create a table at the end of our note sheet just like this to keep track and keep things organized, or you can just label solid, liquid, gas and kind of write the properties in. And so talking about physical versus chemical changes and physical versus chemical properties. Physical properties are more unique to certain substances based on the state of matter they are in. This is like density. Think about when we were talking about density earlier this unit, we can use that as an identification of certain substances if we don't necessarily know the identity. And so those things are unique. And of course, it does depend on the state of matter that we'll talk about a little bit later. Melting and boiling point are also a couple of physical properties there. In terms of the physical change, the outward appearance changes, but the actual inherent chemical composition doesn't change. And so this is a change in outward appearance only. So a physical change is a change in which a substance alters or changes its appearance, but not its chemical composition. All right. An example of this would be a phase change or changing from one state of matter to another, kind of like you're melting or you're boiling, right? Condensation going from gas to liquid, with gas cooling down. Where, again, we know that if we're melting something, well, we're just turning it from solid to liquid, but nothing's changing within the actual chemical makeup itself. It still is the substance that it was before, and it just looks different. Another thing to note for physical changes is that physical changes are reversible, which means if let's take ice, for example. Ice is just liquid water, H2O. If we melt it, then it turns into a liquid form of H2O. If we boil it, it turns into a gas form of H2O. So the chemical composition doesn't change, however, the way that it appears to us does. And those are reversible, right? Phase changes go both ways. So condensation would be the opposite of that boiling. Freezing would be the opposite of melting, and so you can go back and forth. And there, of course, are a couple more examples right there in that diagram just to see, when we're doing something to change how something looks, but we're not changing what it inherently is. In terms of chemical properties, we have things like flammability, how flammable something is, or how readily able it is to combust. So I'll add combustion there, right, to set on fire, to burn, basically. You see we have rotting over there. Rusting is a big one. Rusting, tarnishing is a similar concept there, where we have these things that are occurring that they do not allow us to, one, get that original substance back, right? And so in that case, this would be irreversible. But it's also because that's changing, that it's a change in a actual chemical makeup of what we're talking about. And so the atoms are actually shifting around and forming new bonds in order to create these new things or to look this different way. So it is an appearance change, but in this case, it's going to usually happen what we call spontaneously or suddenly. And so this is a change in which matter is altered and a new substance is created. Something that was not there before. It adds new properties, right, based on what the new substance is. Some signs of a chemical change over here, and you can add that little portion there in that box. Signs of a chemical change are spontaneous, right? These things have to happen on their own. I mean, one of these is color change. Color change. In terms of why it has to happen on its own or suddenly, right? Sudden color change, because I can, of course, go to a wall and I can paint it a different color, but because I did it, it didn't happen on its own. That would be a physical change in terms of a color change. All of these chemical changes are spontaneous, and I want to kind of highlight that too. All right, spontaneous color, let's say, move this, spontaneous color, odor, or energy change. Energy can be in the form of a couple of things. Primarily, we will say heat, so something all of a sudden gets super hot, super cold, and light. There's a burst of energy that you didn't see there before. There are also bubbles, and that is a gas forming. So gas formation there. And we'll talk about solids when two aqueous solutions come together. That'll be a little bit later on. So in terms of kind of what we have now about physical versus chemical changes, we can identify what is a physical, what is a chemical change. So for a silver tarnishing, anything tarnishing is going through a process chemically where the inherent substance is now, the atoms are kind of rearranging themselves, and therefore something new is being created, and therefore that is a chemical change. Whereas cutting an apple, right, the apple is still the apple, it is physical. It just looks different. Iron rusts. Iron is now reacting with oxygen. It is forming something new. Therefore, that is chemical. Alcohol evaporates. The evaporation is the idea of going from liquid to gas on the surface level. Therefore, the alcohol that's now gas is still alcohol by chemical composition. That is a physical change. Breaking glass. Glass is just smaller. Tire inflated. Tire's just bigger, right? Those are physical changes. Digesting food. Sure, you can't get the food back out the way that it was when it went in. So that means that it is irreversible and chemical. Last but not least, woodcut, physical change. All right. And going on to the states of matter, really kind of hitting more along the lines of the idea of physical changes. These are different states that matter can be in. And to go from one to the other would be what we call a phase change. So something like going from gas to liquid is what we call condensation. Going from liquid to solid is what we call freezing. And then, of course, I can go the other way. And I can say going from solid to liquid is what we call melting. And going from liquid to gas is what we call, instead of boiling, let's use a more appropriate term, which would be vaporization. Some might think the water cycle, you might think evaporation. Again, evaporation happens on the surface of liquids, not all the way through, where vaporization is occurring through the entire sample. And so what do models look like for this? And so if in terms of just solids, effectively, they take a shape of something, right? If you look at anything that is a solid, it has a really defined shape. And so these particles that are within these solids are kind of locked into place. Now, it does not mean that they don't move, because these are actually moving, but there is very little motion. Really, they just vibrate back and forth. They can't slip, they can't slide, they can't move past each other. They are locked in place, which again gives this its fixed shape, right? The idea of having a fixed shape means that it stays the way that it is. And because a solid has that fixed structure, the amount of space that it's going to take up is also the same. So it is fixed as well. It cannot be, you can say that it is incompressible. Right? It cannot be compressed. It has to stay, right? So fixed or definite, right? And so we can kind of use those two words interchangeably. So this is definite. Definite shape, definite volume. It is defined. It does not change. Now we get to liquids, right? Liquids, I should also add, just for future reference, the lowest KE, which is kinetic energy, that is energy of motion. So it makes sense that the ones that don't move a lot have that lowest kinetic energy. Compared to now liquids. Now liquids are able to move a little bit more. They're able to kind of slip and slide past each other. They are fluid now, which means that it can kind of take the shape of whatever container it's in. However, they have, they're still close together, right? So they're still close together. They're a little further apart than those solids. They are fluid, like I said, which means that they are moving. They can now move past each other. And if they can move past each other, then they're going to have kind of like the middle kinetic energy compared to all of these, right? The midpoint kinetic energy, if you wanted to kind of say that. And then the volume, of course, if I have a liquid, and let's say a gallon of milk, right? Milk is a liquid, we know that. We know that wherever the milk is, it takes the shape of its container, right? If it's a gallon or a carton. And so no longer is the shape fixed like the solids, because it can move. So we say that it is variable or indefinite, right? The shape can change, right? Liquids take the shape of the container that you pour them into, yet the volume is the same. If I have a gallon of milk in a carton or a gallon of milk in a gallon jug, it looks different because it takes the shape of whatever that container is, but it's still a gallon, right? It's still taking up the same amount of space effectively. Therefore, it has a definite shape, right? It is incompressible. And of course, now we have the gases. The gases are the ones that move the fastest, as noted by these arrows. They are the furthest apart from each other. They have the highest kinetic energy. So furthest apart, fastest moving, most kinetic energy, all right? They have the fastest moving particles there. And because of the ability for them to spread out, not only can they spread out, but then they can come back together. The more they spread out, the greater their volume. The more they come together, the less their volume. So they have a variable or indefinite volume, which means they can be compressed. They are compressible. Think of aerosol cans where there's compressed air inside. And of course, they can take the shape of whatever container they're in, and usually it's to fill it up. And so we say variable or indefinite. So this is just a video version of the notes. You have these. If you enjoyed this, I can do more of these. But outside of that, I will see you later.